Let us look at reefs. What is a reef? It is a mass of organic carbonate buildup by corals, algae or other sedimentary organisms. It can be designated as a member or as a formation. Do not consider a reef as a group or supergroup or as a bed. The geographic names can be used. For example, a reef at some location, Thornton can be called as the Thornton Reef. These organic reefs in more detail are essentially calcareous deposits created by the sessile organisms. They have a long history on the earth, from Archean microbial reefs to the present day coralline algal reefs. This sentence does not mean that some reefs formed in Archean and that continued till the present day. Rather, the context on the earth's surface kept on changing, the environment kept on changing. In Archean, certain reefs were produced, such as the microbial reefs. Now we are getting the coralline algal reefs, and due to much anthropogenic or human activities, these reefs are under stress. And organic reefs can be also called as aquatic biosedimentary structures. There are sediments involved, and also there are some primitive organisms involved in creating them. They form in the water, in the shallow sea, mostly if it is a coral reef. Let us look at the three different kinds of reef geometries. Suppose this is the land side and this is the sea side, and you can see that if this is the water level, there is deeper water levels towards the sea side. Now, in the beach area, we call it a rough water because wave and tide actions are very dominant, and these waves and tides keep hitting the land surface. So, the reefs that are formed, the frame reef, are very robust. They are of laminar geometry. As you go into the deeper water, you get the domical frame reef, and these individual structures are a bit away from each other. Here the strength of water to destroy the reef is much less, and therefore these structures can sustain little bit away from each other, whereas in the rough water condition they are very close to each other, so that they can sustain their presence. As you go to the deeper water, you get cluster reefs. These structures are thinner and they maintain some distance. So, these are the three important terms, and remember, laminar frame reef at the shallowest level, domical reef at little bit deeper water, and at more depth of water cluster reefs are formed. And there is a transition in this way. What I said is from rough water to the quiet water. As you move from quiet water towards the rough water, the relief keeps on increasing, skeleton proximity and interconnection keeps on increasing. As I said, here they were far away, but here they are close to each other. The sediment coarseness keep increasing in this direction, and the water movement also keeps increasing in that direction. What is the meaning of the term stratigraphic reef? They are thick and laterally restricted masses of almost pure carbonate rocks. The stratigraphic correlation of reef is performed using magnetostratigraphy, sequence stratigraphy and chemostratigraphy. These three subjects I will be dealing separately. You can look at my subsequent lectures. When we use the term carbonate mound, we mean it is a build up of carbonate material by the microbial activities. This term marker bed I have explained earlier, but it can be emphasized again. Marker beds are also known as the key beds. They have distinct color or distinct texture or distinct structure or distinct composition, such as an example is given is volcanic ash. They can have distinct color. It can be red bed, it can be red bowl, or it can be black shell. Red bed indicates an arid environment in the past, black shale indicates eosinic marine environment classically, that is how it has been described. Volcanic ash is produced due to explosive eruption, and then the volcanic ash moves up in the atmosphere, settles and works as an excellent stratigraphic marker. Let us learn about the red beds. These are the sedimentary sequence predominantly red in color. However, note that there is a term red bowl. Within the red bed there can be interdigitated drab strata which can be grey, green or black in color. The red color in the red bed is due to the presence of hematite. Fe2O3 is the formula of hematite, rarely because of also the presence of magnetite Fe3O4. These red beds are found especially in the Mesozoic and in the tertiary sections. Red beds can form by different mechanisms. In that case, we use the term polygenetic. It is not monogenetic. Red beds are characterized by positive EH values, neutral to alkaline pH values. They indicate hot surface of the past, which can be continental area or low latitude areas. Marine red beds are rare. The red beds are usually continental. The red beds have been a source of paleomagnetic data. We are going to see magnetostratigraphy separately. Why they are important in paleomagnetic data? Because they have very stable neutral nuclear magnetic resonance NMR. The magnetic property comes from the presence of magnetite and other iron bearing minerals. At the same time, while the NMR study has been done, there has been a debate whether the red beds can really be used for magnetostratigraphic studies. The detrital remnant magnetization, again please look at my lecture on magnetostratigraphy where I have described it, and the post depositional detrital remnant magnetization PDRM in red beds are used in paleomagnetic studies. So, although we are saying it is used, but then at places some researchers have raised question. Growth of orthogenic hematite Fe2O3 in red beds leads to chemical remnant magnetization, CRM or chemical remnant magnetization. Again I have discussed in magnetostratigraphy section, please have a look there. Use of unconformity, I have already said groups and subgroups can be defined based on the unconformities present at the top and at the bottom. So, they are the ideal boundaries for the lithostratigraphic units. They can be traced laterally. Now, to identify the lithostratigraphic units, one can go directly in the field, but then the amount of area covered per day will be less. It is recommended that before going to field, one looks at the remote sensing images where a vast area can be covered very quickly on the computer screen, and this will be an indirect evidence of study. In the remote sensing image, one can note the distinctive vegetation that may indicate if there is plant A at one place, plant B at another place. Two different lithologies may be present, but needs to be cross checked in the field. Going by the indirect evidence, one can look at the geophysical data set. One is the electric log, the other is the seismic reflections. While talking about the unconformities, I have shown you some seismic images and various unconformities. You can look at my lecture on unconformities to find out the seismic images. In the geophysical data, we will also count the image log, and I would request you to look at my drill core related lectures in this stratigraphy series. Certain terms are discouraged to use in lithostratigraphy, for example, soft, hard, folded, brecciated, etc. If I say a soft formation, it is not very useful, because what is soft? Some rock which is soft, tracking it horizontally one can find it has been hardened. Same problem with the hard. The layer which we are calling as folded, if at all we are describing, we may find that after some distance tracking horizontally, their layer is no more folded but is horizontal. The rock can be brecciated, that means crushed due to the presence of faults, but that is not a characteristic point to talk about the lithostratigraphy. Suppose we are discussing some formation, X formation repeatedly, then after first writing X formation, we may write the formation, and this is acceptable. For the beginners, it is important to tell if a source of sediment is at location X, say this is a source rock and here the deposition has happened and the location is X, the deposits we find and we work out by provenance study it has come from X in the past, we cannot call it in the past, we cannot call this formation as X formation, not permitted, that is what is said here. X should not be used in naming the unit. Use Y, the location where it is found. Suppose this location is Y, then we can call this as Y formation. Provenance study has its own use, but the provenance is not reflected when we write, let us say, K formation. This means K is the location where this formation is best exposed. Here K is not the location from where sediments came. The same name is not to be used more than once in the lithostratigraphy of an area. Suppose someone says Kamlial formation, which is actually present within the Shivalik supergroup. Then do not use the term such as Kamlial group. This term does not exist in the stratigraphy. There are terms such as lower, middle and upper. It is recommended not to use as a formal subdivision of a lithostratigraphic unit. If I say X formation and then I say lower X member and then upper X member, it is recommended not to practice such a nomenclature, or X group divided into upper X formation and lower X formation should be avoided. Let us look at the spelling issue. A stratigraphic name repeatedly published with a spelling different from its geographic source should be retained. What it means? Let us take the Bennett shell. This term has been used and published for few decades, and then the word Bennett is actually coming from the town Bennett, and you can see the spelling difference. Here it is Bennett, here it is Bennett. So, it is recommended to keep on using this term and do not go back to this spelling while referring the shell. That means, if someone is now writing is making a mistake and is not recommended. Words should not be translated from the already used term. In the stratigraphic name, let us say X formation, say X is a word and it is, let us say in French. Keep using the term X formation, do not translate X from French to English. Change in name of city should not be reflected in the stratigraphic name. Suppose we are calling a stratigraphy unit as X formation, X is the name of a city and the name subsequently changes to Y, then the formation name should be retained as X formation. This can be comparable with, let us say, X university, and then the name changes, the city name changes from X to Y, we nevertheless call the university as X university. Lithogenic terms such as turbidite, flysch should be avoided for formally named lithostratigraphic units. We should not use the term turbidite, we should not use the term flysch within the lithostratigraphic description. In the study of stratigraphy and sedimentology, it is very important to have the basic understanding of geosyncline. This concept has vastly been modified, and in the light of plate tectonics, people have explained geosyncline recently in different ways. However, the concept is somewhat obsolete. We need to know at least the basic of geosyncline. James Hall noted in mid 19th century from the Appalachians that the thickest sedimentation happened in the deepest part of the basin. What does it mean? Suppose I have drawn a basin. So, here this portion of the basin is the deepest part, and in this sedimentary basin, suppose the water level is shown over here, then it was observed, generally speaking, that the thickest layer of sediment is deposited where the basin is deepest, and where the elevation of the basement has increased, here the thickness is reduced. So, also over here. Now, why this happens? Consider a basin, consider there are sediment particles. Sediment particles will be deposited vertically down in different places. Those sediments which are deposited in the flank over here, there is a good chance that by gravity they get transported and go to the deepest part. So, from here also it can go to the deepest part. So, this can be one of the reasons why thickest sedimentation happens in the deepest part of the basin. And it was also inferred in James Hall time that large scale sedimentation that eventually form the mountain belts occur along linear troughs and along the continental border. At the margin of the continent, there can be linear trough. This can be linear region where there can be depression inside. And in these troughs, sedimentation took place, and eventually this became the mountain belt. It is not clear in the geosynclinal concept why here only the mountain belts will be produced. Many of the mountain belts are long linear zones. If I take the Himalayan mountain chain, the Pakistan sector, the Indian sector, then Nepal, again Indian, and then Bhutan and again Indian sector, and then the Myanmar sector. And then there are longitudinal strips of similar lithology which are present, more prominent in the Indian Himalayan sector, and this linear longitudinal division of the different units of Himalaya such as the Shivalik, Lesser, Higher, Tethyan and Trans is not so well discriminated in the Pakistan sector over here. When we say Himalaya geologically, we include the Pakistan sector and the Indian sector, and when we say Himalaya in the geographic sense, we also take this Myanmar sector. Geologically, we do not call this sector as the Himalaya. So, at least in the Himalayan region of the mainly in the Indian sector, we get long linear belts of sedimentary basins. For example, the Tethyan Himalaya and the Lesser Himalaya, also the Shivalik Himalaya, which is an ancient foreland basin. So, the examples of geosyncline come from the Appalachians, and also Alpine Himalayan belt, Alps and Himalaya have also been considered as examples of geosynclines. There are several old research papers available, and Auboin in 1965 made a review concept of geosyncline and also its occurrence in various places in the world. Now, let us look at a cross section involving the continental crust and the oceanic crust, and try to understand how the geosyncline was conceptualized in the past. Here this domain is the foreland, and here this portion we think that it is an oceanic crust. We consider a Sialic basement, and in the left hand side here we are considering a continental crust. Now, here the basement is elevated and depressed. Here This is the greatest depression. So, we expect here the thickest sedimentation to happen. From this place to this place approximately is a place of deposition, and we call it as a myogeosynclinal furrow or simply a myogeosyncline. Then this elevated portion, and it is called genetic line, also known as myogeosynclinal ridge. As we go from myogeosynclinal ridge towards the oceanic side, this is the oceanic side, we come across another depression where sedimentation can happen, and this depression is called the eugeosynclinal furrow or simply the eugeosyncline. Then again there is a ridge which is known as the eugeosynclinal ridge, which is also known as the borderland. In the flank, ophiolite can be found, and within the eugeosynclinal furrow a special kind of sequence of sedimentary rocks has been identified, and it is called as flysch. We are going to see the Boma sequence, which is important in stratigraphy and sedimentology. First of all, where it is found, we find in turbidites. So, essentially we may encounter it in the submarine fans, and it can be the deposition of a mass flow. It is a non-cyclic deposition. We are not going to see in case of Boma sequence AB this kind of repetition. So, it is a non-cyclic deposition, and even though we will idealize by saying that there can be 5 important layers, some of the layers might be missing. At the bottommost as one can be graded or massive beds. Massive means that the deposited sediment does not have any internal structure, no bedding plane or no lamination. But there is another possibility that it can also be graded deposit. Next, we get parallel laminations with as a second layer. We are calling it lower division. Why? Because in number 4 we get the same thing as the upper division. Above the layer 2 comes current ripple lamination, which can indicate the flow direction. Now, over layer 4 comes the pellitic division. Fine grained sediments get deposited. So, as I told you, not that everywhere in the Boma sequence will be fully preserved like 1, 2, 3, 4, 5. It is also possible to have 1, 3 and 5 vertically up, or we can get say 1, 4 and 5. Some of the units might be omitted depending on the actual flow and the deposition condition. So, in these 5 units, what gets repeated is the parallel laminated unit gets repeated. No other units get repeated in the ideal Boma sequence. Do not expect that in every submarine fan, in all the mass flow deposits and in all the turbidites, such a sequence will perfectly be preserved. Suppose you get like this 1, 2, 3, 4 and 5 in a vertical succession. So, this will indicate an inverted Boma sequence. One comes across the term Boma sequence. Let us see the turbidite and Boma sequence together in a slide. Classically, the Boma sequence has been described from the deep marine environment, where the water is tranquil. Several layers Ta, Tb, Tc, Td and Te have been worked out. But subsequently it was found that the Boma sequence may not be found as it is in the exactly the same form which is shown over here, Boma 1962 classic paper, in all the deep marine deposits. At places different Ti is disputed. Come to turbidite, these are the deposition of turbidity currents, gravity driven turbidity suspension of fluids, kind of subaqueous flow. Mud to gravel size sediments get deposited, very fine grained mud clay size particles or gravel gets deposited. It can be siliciclastic or carbonates. Do not think that all the turbidites are siliciclastic. The diameter of the grain can be millimeter to tens of meters. In stratigraphy, turbidites are studied by chemostratigraphic approach. Chemostratigraphy I will be discussing in separate lecture in detail. The correlation of turbidites can be found in research papers. I have referred one, interested student can go through. Different orders of correlation of turbidites have been made. The first order correlation is based on the age or geochronology, which means lithostratigraphy is not applied, rather chronostratigraphy is used. In a separate lecture, I will be talking about chronostratigraphy. The second order correlation is by correlating the beds, the different beds. The lowest unit of lithostratigraphy is correlated, and the third order correlation is in terms of facies. Facies indicate in this case a group of rocks indicating similar environment. So, the age has been used, the lithostratigraphic units and the smallest lithostratigraphic units has been used as bed as a second order correlation, then facies as a third order correlation. These three approaches are used in correlating the turbidites. At some point we will touch the term flysch. It is a thick sequence of syn orogenic turbidites. Flysch has been described as a kind of turbidite. Syn orogenic means simultaneous to orogeny or the mountain building process. I write here the flysch sedimentation as per the geosynclinal concept can be found within the eugeosynclinal furrow and not in the myogeosynclinal furrow or within the myogeosyncline. Molasse, these are the late orogenic detrital deposits. Molasse from an orogen comes later than the flysch and they develop in the 4 dips in the flanks of the collisional orogens. An example is the Shivalik group. The southernmost portion of the Himalaya is described as molasse, sediments shed by collision of the continental plates. Molasse, what is this? It is a product of post orogenic sedimentation. What does this mean? After the mountain has formed, if any sedimentation takes place, it is known as post orogenic sedimentation. That means this is after mountain formed, if any sedimentation happens, then it is known as the post orogenic sedimentation. What do we get in the molasse deposit? Several sequences of fining upward fluvial and deltaic cycle, and we can have conglomerates with well rounded clasts. An example of molasse can be the Shivalik deposits, which is the southernmost part of the Himalaya. The present geoscientists may not use flysch and molasse words to describe some deposits, but in the old literature we do see examples of flysch, molasse and geosyncline. To read old literatures, this much of information is required in stratigraphy and in sedimentology. When we study the facies association, Walther's law is very important. The facies association that passes side by side, which I will explain, also preserves vertically, not always but in many cases. So, what it means? Suppose in a map you are observing 3 lithologies, sedimentary rocks occurring side by side. So, this is the map view, or we can say plan view. Say the left hand side is the land side and the right hand side is the sea deposit. In this case, it is possible that layer C was the earliest to deposit, layer B was next to deposit and A is the youngest deposition. So, this is the vertical succession. Now, look at this statement. If I call this side by side occurrence as x and vertical occurrence as y in a succession, if I know x, I can comment about y, and vice versa. If I know y, I can comment about x. Now, this law works for fluvial sedimentation. It cannot be taken as a general condition and be applied everywhere. Another important point, limitation of the Walther's law, where it works and where it does not work. It works if the succession is devoid of any unconformities. That means, in this vertical succession C, B and A, none of these contacts are unconformities, they are conformable contacts, which means if there is a time gap in deposition between C and B, then this becomes unconformity. This is not the case. If there is a time gap in the position between B and A, then this becomes an unconformity, and that is also not the case. If there are unconformities, then Walther's law cannot be applied. That means, in a coastal region, if you are getting rock M, N and R and you find out that here is an unconformity, that means you cannot apply Walther's law here. In other words, from this given vertical succession, you cannot predict the side by side occurrence of different rocks.